Well, first of all, thank you for inviting me to this seminar series. I'm very glad to talk about petit-spot volcanoes, and which are these relatively small volcanoes that form on the incoming plate of subduction zones. And I hope that I will give you some hints about their relationship to plate bending and subduction earthquakes. Most of my talk will be focused on the results of IODP Cube Expedition 502, which was occurring last November. So I will give a brief overview of what is petit-spot volcanism, the objectives of Expedition 502, some details about the operational plan, and some first onboard results. I will show you some rocks at least that we recovered. So first of all, what is petit-spot volcanism? These volcanic clusters, which are formed by small monogenic basaltic volcanoes, which are just a few kilometers in length and about 300 meters high, have been discovered mostly on the western side of the Pacific plate. And you can see here some of the sites where they have been found. In particular, we will concentrate on this site C, which was also the area that was targeted by IODP Expedition 502. And you can see from this enlarged map that they are really small bathymetric features, and all of them here have an age that is less than 2 million years. 2 million years. And these are basically on the outer rise of the Japan Trench. So the Japanese colleagues have carried out several dives to look at these volcanoes on the seafloor. And you can see here some pictures from the lava flows on the seafloor. And from this hand specimen, you can see the basalt lava with some big, actually, xenolith of peridotite, some xenoliths of olivine. You can see some quenched edges with glass and some haloclastite. So this is sort of what we knew in terms of geology of these volcanoes before Expedition 502. And from a petrological point of view, and I'm sure then Sebastian will actually go at much more in detail about this, we know that these magmas are highly alkaline, with they're very rich in CO2, and for this reason, actually for their geochemistry, we can trace their origin at the lithosphere-asthenosphere boundary. And the sort of tectonic reasons why we find them on the seafloor as volcanoes is related to the bending of the plate before it starts to subduct, so that we have basically a concave flexure of the downgoing oceanic plate that is producing some fracturing at the base of the lithosphere. As the plate then bends, this magma can rise up. And we have targeted these petit-spot volcanoes for drilling as they are sitting on the outer rise. The interesting modifications that this petit-spot magmatism brings to the incoming plate is that basically they completely change the stratigraphy of the incoming plate. So here you can see on the right-hand side of the slide a sort of a typical West Pacific plate stratigraphy. So the igneous crust and then chert, and then this smectite-rich clay layer, which has been targeted also previously by ocean drilling because is thought to be one of the key players in seismogenesis when looking at the co-seismic slip, for example, of the Tohoku earthquake. And then on top of this smectite-rich layer, we have the mostly siliceous sediments, more recent siliceous sediments on the Pacific plate. As the petit-spot magmatism start to occur, we have big changes occurring to this stratigraphy, not only because of the magma itself and the seals and the lava flows, but also because we start to have a strong fluid rock interaction. The sediments can get much more consolidated, alteration, and so basically, what we have here, for example, in D, as the normal stratigraphy, the normal input into the subduction system, we can get it very altered by this time we go into the trench for the effect of this magmatism. So the objectives of IADP Cube Expedition 502 were to determine whether these petit-spot volcanism was widely distributed and how they can affect, for example, the global volatile cycle, CO2, but also other volatile elements, to look at how this magmatism could affect the subduction zone earthquakes. So when they enter into the subduction system, what is happening to the megathrust and how the, for example, megathrust earthquake can be affected by this change in physical properties of these incoming sediments. And then the subduction factory as a whole, and so the cycle, the global geochemical cycle at depth. Here are some examples of material that has been recovered from the Japanese dives before drilling. You can see this breccia here. This is a rock called pepperite, which is basically a breccia of magmatic material within these altered sediments, some of them poorly consolidated, some of them altered and consolidated. So these perturbation, these sediments that are working as input into the megathrust really can change the mechanics, the mechanical properties of the host rock in the megathrust. Another more regional overview about what is happening can be given looking at these maps, which are reporting the depth of the acoustic sediments, for example, here to the left. This area, TPC, is the site C that I was showing before, is the target area for the drilling. And you can see here that basically the acoustic basement is really changing in depth, being really shallow in the area that was targeted for drilling, and being less, deeper in the adjacent areas. If we look also in another perspective to this data, and we sort of put instead we want to look at the thickness of the sediments, and we take as a normal sediment thickness to be about 500 meters. We see that in this area, the sediment thickness is indeed quite small. So we have wide areas with relatively shallow acoustic basement, and this can be related to the slip distribution of the 2011 Tohoku earthquake, which you can see here in this picture, but I'm going to show you much better in the next slide here, where we can see to the left the in this area with the blue contours, the area which was the rupture area of the 2011 Tohoku earthquake. And these blue lines means that the P wave velocity of the area is actually quite high, and which means that we have a denser and stiffer material here in agreement with both a magmatic host rock, or rather a sedimentary rock which has been consolidated, which would be in agreement again with this alteration, perturbation brought by the petit-spot volcanoes. And here in the center, you can see again, maybe enlarged, the co-seismic slip area for the Tohoku earthquake. And again, this picture that I showed before, which actually shows that there might be a correlation. And this is one of the hypotheses that were brought forward during Expedition 502, and that we would like actually to test with the sediments and the rocks that we recovered. So some ideas on the operational plan. Here we are in this site C. We targeted a small petit-spot volcano. You can see here on the right enlarged. We drilled 6 holes and around the slope of this petit-spot. And here I can give you some ideas of the operation. This is a video shot while we were drilling. You can see the heavy rains. We had 3 typhoons actually hitting us during the expedition, but drilling continued. And here you can see the derrick, the rig floor, and here, and the pipes. Basically, when the material is recovered, is then the cores are put in these big trays and then transported into a lab that is taking care of, first of all, cutting these 10 meters long core in sections of 1.5 meters. And the first sampling, the time-sensitive sampling, is actually occurring in this first, well, basically when the core is still outside, in this outside lab. Just to give you an idea of the material that we recovered, we were able to drill a little bit more than 100 meters below seafloor. And the material that we recovered was about 60 meters of sediments on top of 45 meters of basalt. The sediments were basically siliceous mud, meaning that they were formed by volcanic and biogenic silica and clays. And you can see here that this material is divided in 2 units. And the difference is really the occurrence in the lower part here of many ash layers. Unit 2 was also divided in 2 subunits based on a dramatic change of colors that I will show later. But no difference in composition, at least what we could do on board. So let's look at these sediments. Here are these grayish green siliceous mud. You can start to see some of these ash layers. Here you see some of the sampling that was already done on the cores, and a close-up on one of these ash layers. So you see that they are quite light in color. We think that they are coming from the Japanese islands. And if we look at this change in color, you see that is quite sharp. We thought at the beginning that this was related to some sort of alteration from the petit-spot magmatic activity, but actually we were not able to see any evidence of this, and we think that this is more related to some climatic or oceanographic reason. The contact with basalt was recovered twice. You can see one of them here. On top of these basalts, it was recovered a breccia, but I would say rather a drilling slurry. This was really very deformed by drilling disturbance. While the second contact is much cleaner. You can see basically a nice contact, even though it's all in pieces. And probably there is some breccia here, but it is much better kept, is not completely destroyed. I should also add that drilling these basalts was basically the hardest material that I have ever found while at sea. You can see here some of the before and after condition of the drill bits. This is the logging bit, and this is the drill bit. And you can see that in both situations, they were highly damaged just after a few hours of drilling. To finish, I just want to show some pictures, thin sections and hand sampling from these petit-spot basalt. You can, starting from the left-hand side, you can see some subhedral to skeletal olivine phenocrysts within a ground mass that is actually highlighted here in the center, that is formed by acicular and dendritic olivine and clinopyroxene. And here on the right, you can also see some acicular oxides embedded in glass. From the hand specimen, you can see some vesicles, some of them filled up by some alteration material. And well, I'm sure that Sebastian will actually go much more in detail about the characteristics, the geochemical and petrology of these basalts. So I will stop here and thank you for your attention.